Good afternoon, everyone. It's exciting to be here. So this work is a collaboration between Purdue University, Google AI, and the TensorFlow team. So in this paper, we propose a new methodology for expressing machine learning models in Python. We demonstrate this methodology using source code transformation and dynamic dispatch to enable multi-stage programming. We describe AutoGraph, a system we implemented for this purpose, and we show that it allows writing expressive machine learning code which retains the performance and portability benefits of graph execution. To motivate our work, I would first like to talk about a few of the current challenges in machine learning development. I will focus on the Python language and more specifically on lower level development of writing more complex, newer machine learning algorithms. We can distinguish two major paradigms that are widely in use today, as we've seen in the previous talk as well. One of them is imperative execution, also known as define by run. This paradigm represents the classical way of running a Python program. Operations execute immediately, and results are readily available. This is a very practical way of prototyping new models, and it integrates well with existing tools and APIs. However, programs written for imperative frameworks tend to be seen as more challenging to export and optimize due to the dynamic and interpreted nature of the Python language. Another paradigm is graph-based execution, also known as define then run. Python, in this case, is used as a meta-programming language in which a computation graph is first being built and then executed. Computation graphs, much like compiled programs, tend to benefit from additional optimizations. They are also portable and can typically be deployed to a variety of platforms ranging from embedded devices to large-scale distributed systems. However, graph-based programs tend to be more difficult to write and maintain. For example, they require control flow to be expressed in functional form, which is more verbose and less readable, and it's particularly cumbersome when nested. So given these two paradigms, there appears to be a trade-off between ease of use and performance or portability. With AutoGraph, we aim to combine the benefits from both. For the majority of this talk, I will focus on the utility of AutoGraph within TensorFlow, for which we optimized it. But we believe the method can be applied more broadly within the Python language, and we'll demonstrate that towards the end of the talk. AutoGraph works by converting imperative style code, as shown here on the left, into graph code, shown on the right. This allows developers to write more expressive code that can still be executed as a graph, thus gaining the benefits that come with it. Now, we just attended a great presentation of TensorFlow Eager in the previous talk. AutoGraph and tf Eager serve complementary roles towards improving the development experience in TensorFlow. While Eager makes graph execution seamless using the tf.function API, AutoGraph focuses on allowing a more expressive syntax within the tf function. In fact, tf.function is now the recommended way to use AutoGraph in TensorFlow. Here we have an example. If you focus on the body of the function, notice that there is a Python while loop, which is conditioned on a tensor expression. This would normally not be allowed in graph-based code. AutoGraph will convert this to an actual tf while loop API call. Then the tf function decorator will add the necessary instrumentation to the function so that when called, it will seamlessly be converted, traced, cached, and executed as a graph. AutoGraph can also operate in a standalone manner if for any reason tf function cannot be used. In this case, which shows the same function as before, AutoGraph converts it into a new function. This new converted function can be used like regular graph code. Next, I will describe some of the more important techniques that enable this. But first, let us know that AutoGraph supplements the existing operator overloading mechanism found in Python. This mechanism is already helpful in allowing a more natural expression. For example, because the tensor class defines the necessary overloads, arithmetic expressions on tensor objects can already be written using a natural form. However, the standard operator overloading does not extend to control flow in Python. In other words, we cannot write these kinds of overloads. AutoGraph fills this gap by replacing control flow like if and while statements with equivalent function calls. These function calls serve a role that's very similar to that of overloaded operators. In essence, AutoGraph is a transpiler. It converts Python source code, typically in the form of a function, into equivalent graph code. This is achieved using source code transformation, a technique we previously applied in Tangent. It consists of parsing the source code of an input function into a Python abstract syntax tree, then incrementally and repeatedly transforming this AST so that ultimately it can be used to construct a new function. All this is done at runtime. Importantly, the Python runtime, the standard Python runtime, provides all the facilities critical for this process. And this allowed us to implement AutoGraph entirely as a Python library. An important challenge with machine learning code is that it tends to mix effective computation with setup and configuration code. Here's an example. If we focus on the control flow in this example, the for loop and the if statement at the top rather serve a role in describing how the computation should be constructed. And only the for loop at the bottom is part of an actual computation. This pattern bears a strong resemblance with staged programming, which has been previously studied in the context of other programming languages and has been made popular by work such as lightweight modular staging. Traditionally, staged programming identified two stages, compilation and runtime. But we can recognize them here as graph construction and graph execution. During graph construction is when Python code actually runs. During graph execution, control is handed over to a downstream system outside Python, typically the TensorFlow runtime. So in this case, we could state that when an op is being called in graph code, the respective computation is being staged for graph execution. Given that, we now have to make a decision then when transforming code. That decision is whether to stage a particular construct or not. A reasonable heuristic, one that is also consistent with the standard operator overloading, is to do it based on the type of the operands. For example, it is reasonable to consider that a for loop should be staged if it iterates over a tensor. Our type-based dispatch follows this heuristic as well. It will create a TensorFlow op whenever the statement depends on a tensor, and otherwise it will revert to normal Python execution. Now, a further complication arises from the dynamic nature of Python. Inferring the type of a variable cannot be done robustly just by looking at the code. For instance, the return value of this getRange function here could have just about any type. To solve this, we instead use dynamic dispatch. All the AutoGraph will rewrite all the control flow statements with special AutoGraph functions, which will examine the type at runtime when it's actually known. This example shown here is a depiction of AutoGraph's actual handle for if statements. Notice the decision to construct a TensorFlow op based on the type of the condition argument. If the condition is not a tensor, then the transformed code will be functionally no different than the if statement which it originally replaced, although it will execute with a small overhead. But we are not worried about this overhead because it influences the graph construction and it does not impact the graph execution. There are also certain Python statements which cannot be easily rewritten as functions. Examples include non-local control flows such as break, continue, and return. We handle these statements by rewriting them into equivalent lower-level code that relies solely on extra conditionals and signaling variables. This new resulting code is then converted normally. Function calls represent another important idiom. It would be quite impractical for AutoGraph to require that each and every function be explicitly converted. Instead, we rewrite function calls with a special wrapper. This wrapper will typically convert the function at runtime. However, it might also decide to call the function unconverted, for instance, if it's a TensorFlow library function or if it's of an unsupported type. Lastly, statements which AutoGraph does not currently handle, typically because they have no equivalent in TensorFlow, are left unchanged in the code. This allows AutoGraph to accept a very large subset of the Python language as input. including existing TensorFlow graph code. Next, I will show a few of the use cases on which we tested AutoGraph. The first one being an in-graph training loop. And we found this example to be interesting because AutoGraph facilitates the expression of control flow, and the training loop is essentially just that, a loop. Here is shown the most relevant portion of the code. Notice the for loop iterating over a tensor. Also notice calls to standard TensorFlow API like optimizers and iterator. Performance-wise, the AutoGraph version of the training loop is roughly twice as fast as an equivalent training loop written in Eager. But perhaps more interestingly, the in-graph training loop was also faster than the traditional method of training models in TensorFlow, which is using repeated calls to the session API inside the Python loop. We believe that's because the TensorFlow runtime is able to further optimize the loop itself. Another more complex use case is an implementation of the L-BFGS algorithm, which is non-trivial even in its simplest form. It makes use of a circular buffer structure as well as nested control flow. In this particular instance, we ran the exact same code twice. First in eager mode and then in graph mode via AutoGraph. Once more, the AutoGraph version was about two times faster. A final example which demonstrates how AutoGraph can be applied more broadly. In this case, we replace AutoGraph's code generation of TensorFlow code with an S-expression generator. S-expressions are a grammar useful for representing programming languages. For example, we can use it to represent the reentrant function calls that you typically find in a 3RNN model. And we have here an example of S-expressions on the right. Then we wrote a parser which took the S-expressions and converted them into Scala code targeting the Lantern backend, which in turn can generate C++ code. The net effect is that we have a Python frontend for C++ code. In closing, a few words about possible future directions for AutoGraph. We are currently working to make the core of AutoGraph available as a standalone library to be available for other uses. We also plan to add support for more Python constructs as well as more staging patterns. And I would like to mention here that perhaps you've seen the Janus demo yesterday. We are particularly excited about the new features that it proposes. We've also spent a great deal of time and we've dedicated a great deal of effort on testing AutoGraph, and we continue to improve it. However, a formal proof of correctness remains a topic of future work. We'd also like to make it easier to debug AutoGraph code, and to that end, we are working on improving things like error reporting. AutoGraph is currently in beta, but it is stable enough to try out. It is available as part of the TensorFlow library, and the stable version of AutoGraph, which focuses on control flow, will be available in the TensorFlow 2 release. In conclusion, I presented AutoGraph, a system which lets you write faster and better machine learning code. It will be available in the TensorFlow 2 release within the tf.function API. And although the implementation specializes on TensorFlow, the method could be extended to broader Python applications. If you'd like to learn more, check out the TensorFlow documentation and the examples on GitHub. And we've also loved to hear your feedback. And you can reach us through the TensorFlow community site. Thank you.
All right, we have plenty of time for a few questions. So I'd like to ask, how does the framework integrate with fault tolerance primitives? Like if you run something on like multiple GPUs and one fails, is that accounted for, or is it yeah?
It integrates in the sense that in the same way as regular graph code integrates. Basically, if you add the necessary constructs within the code to account for those scenarios, then it will work properly. Basically, it supports everything that TensorFlow supports, every primitive that TensorFlow has.
Yes, please.
Can we go back to the slide where you converted Python to C++? You went through that quickly. I wanted to look at. So if you had like a TensorFlow up inside the Python function, let's say matml, does it get converted into like another TensorFlow function in C++ as well, or is it getting native code and
That is a good question. I'm not sure whether we have the functionality in there to convert calls to the TensorFlow function into corresponding equivalent C++ calls. I can follow up afterwards to tell that for sure, but I can definitely say there is no reason not to be able to do that.
Okay. And the second question was like, are you only targeting C++ or are there plans to support other backends in the future?
Can you repeat the last part, please?
Are there any plans to support other backends in the future, or is it just C++?
So this example was more like an example. I'm not sure that AutoGraph in the release version will support targeting C++, but what we intend is to make it generic enough so that if you would like to add your own backend, we want to make it very easy for you to do that.
Okay, thank you.
All right, let's thank Dan again.
Thank you.